Alright, AP Statistics. Going back a little bit to sampling distribution models, because really this is the important piece that we need to understand before we move into inference. Everything that we do from here on out is going to be based on a sampling distribution model. Basically, a model of different sample statistics that we take. So before we get into that, we have two types of data. We have categorical and quantitative. Remember, categorical data is our counts. Those are always whole numbers, and we represent them with proportions or percents. We can organize them on a contingency table, and we can display them on a bar chart, pie chart, or if we're dealing with two or more categorical data variables, we can use a stacked bar chart or side-by-side bar chart. If we're dealing with quantitative data, remember that's measured, and it generally has something that has units like inches or feet or gallons. We organize them into a frequency table. We can also make a relative frequency table, and we can display it in a picture on a histogram or a dot plot or a stem and leaf plot or a box plot, each having their different advantages. So the notation that we have to make sure that we're also solid on is the difference between a parameter and a statistic. So remember, a parameter is something that's unknown, and we use a parameter. So this is something that's unknown. However, we try and estimate the parameter from a statistic that's something that we calculate. So if I'm talking about a parameter for a mean, I'm going to use mu. If I'm talking about for a statistic, I'm going to use x bar. Standard deviation, I'm going to use sigma. And then if I'm talking about a statistic, S of x. If I'm talking about a proportion, if I was to follow the pattern that we've established with using Greek letters, I would use pi. However, a lot of people, instead of using pi, since pi has a very special place in all of our hearts, we use p. And if I'm dealing with a statistic, it would be p hat. Remember, parameters are unknown. Statistics are something that we calculate from a sample to try and estimate the parameter. So if I'm dealing with a sampling distribution of proportions, if I was to go ahead and take repeated samples, all of the same size, and calculate their proportions, remember a proportion is something that I can think of as being one of two things. Either you're orange or you're not orange. Either your house has lead paint or doesn't have lead paint. Either you want to vote yes on the proposition for the school budget or you don't. So think of a binomial distribution. That's stuff that we all learned about in the last chapter when we were dealing with random variables. A binomial distribution. So going back to a sampling distribution of proportions, if I was to draw several thousand sample proportions, all of the same size, and I was to plot them into a histogram, the shape would be unimodal and symmetric. In fact, if I drew enough samples, it would look normal. The center of my distribution would be P, or close proximity to P, so my parameter P. And it would follow that I would have the normal model of P and the standard deviation square root of PQ over N. Remember, Q is just 1 minus P. So here, if I was to look at just a regular binomial distribution like we did in the last chapter, remember that our standard deviation was the square root of NPQ. Now when I'm looking at the standard deviation of my p hats, so of all my sample proportions, I'm going to divide by my sample size, and that gives us the square root of PQ over N, which gives us this model here. Of course, to be able to use this model, I need to check a couple assumptions. First is that the individual values, or the sampled values, are independent of each other. So that's one assumption. And the second assumption is that my sample size is large enough. Both assumptions are really hard to, well, it's always hard to make an assumption, so we have to check some conditions. And the first condition, and two of the conditions actually seem to contradict each other. The first one is that our sample is less than 10%. So, for example, if I was to draw some M&Ms from a bucket of M&Ms without replacing them, I need to make sure that my sample size is less than 10% of all the M&Ms that are in that bucket. The second condition that flows from the assumptions is that I need to make sure that my number of possible successes in my sample and the number of my possible failures are both greater than or equal to 10. So they seem to contradict each other. I want it to be large enough, yet not too large to not be independent. Next, we can also look at a sampling distribution of means. So I can kind of make the same argument that I did in the last case. If I go ahead and draw a bunch of several thousand samples, and I compute the mean of each of those samples, and I plot them on into a histogram, it would be approximately normal, and the center would actually be at mu. Now here, remember the standard deviation for each of those individual samples would actually be S. So our standard deviation would be S of each of the samples. Standard deviation of the population, remember, is sigma. And if I wanted to find the standard deviation of my sample distribution of all those means, it's going to be my population standard deviation all over n. Now, a lot of times we don't know what sigma is, and in that case we end up using the standard error of our sampling distribution of means, where we'll use one of our samples, compute the S, and divide that by n, and that gives us a reasonable estimate for the standard deviation. All right, well, I hope you enjoyed the review of Chapter 18.